My name is Yuan, and the topic we are doing is flight/jetpack. The part I am in charge of is theory. When choosing between 2D versus 3D, one of the reasons is the X, Y, and Z axis. In 2D games, the X axis represents horizontal movement, so for a typical 2D side-scrolling game, moving to the right increases the X value and moving to the left decreases it. Moving them right moves them right, and moving them left moves them left. The y-axis represents vertical movement. Moving up increases the y value and moving down decreases it. As you can see from the GIF here, the player is moving up and down along the y-axis. But in 3D games, the x-axis still represents horizontal movement, but in 3D it typically refers to left and right movement. The y-axis refers to up and down movement. The axis introduces steps into the game. Moving along the z-axis could mean moving forward or backwards relative to the character's perspective. This axis as the third dimension of depth. Another reason is the camera and controls. In 2D games, there are different camera systems like scrolling camera, where the camera follows the player horizontally, keeping them in view as they move through the game world. Another camera is top-down camera. This camera provides a bird's eye view of the game world, allowing the player to see surroundings from above. In 2D games, the player is usually limited to left, right, up, which is jump, and down, which is crouch or descent. And in most 2D games, the player does not control the camera and the camera movement is automated and tied to the player's movement. In 3D games, there are camera systems like first-person camera, first-person camera, which provides the player's perspective as if they are looking through the eyes of the character. Third-person camera, which shows the player from a distance, usually from behind or above. Free camera, which allows the player to move independently of the character. Movement in 3D games include forward, backward, left, right, and often up, jump, and down, which is crouch. The player often have direct control over the camera. This is our problem statement, which is when we are implementing flight into a 3D game, we want to simulate realistic movements while airborne and implement a control system that allows player to manipulate that movement. These are all the first math we have is Newton's first law of motion, which is the first law is inertia, which means that an object will stay at rest or in motion unless acted upon by an external force. Newton's second law, force accelerations, which means the acceleration of an object depends on the force acting on it. And the third law, which is action and reaction, which means that for every action there is an equal and opposite reaction. So now let's go down to see how this applies to our problem statement for aircrafts. So for the first one, drones. The first law states this means that for drones, they'll keep flying at a constant speed and direction unless forces like gravity, air resistance, or air engine thrust come into play. The second law, which is for drones, is changing the speed of the rotors changes the thrust and consequently the acceleration. And for the third law, when the drone rotors push air downwards, the air pushes back with equal force, creating lift. For planes, the first law is that they'll keep flying at a constant speed and direction unless forces like gravity, air resistance, and engine thrust come into play. So for the second law is for planes, engine thrust propels them forwards, while the lift force generated by the wing is needed for ascent. And the third law is that the engines thrust air backwards, which propels the plane forward. So that's how it shows the action and reaction. For glider, it's the same, which is they will keep flying at a constant speed and direction unless forces like gravity and air resistance or engine thrust come into play. For the force and acceleration, for the second law, although gliders do not have engines, this law still applies. Gliders must maintain a certain speed to generate enough lift to counteract gravity. Pilots can control acceleration by changing the glider's orientation to use gravity. And the third law, which is, even though the gliders lack engine, they still follow this law as the air pushing back against the forward motion helps generate lift that keeps them in the sky. To understand how drones, planes, and gliders fly, we need to look at the four key forces: lift, drag, thrust, and weight. Lift is the force that allows aircraft to rise, while drag is the force that acts against the aircraft's motion, which slows it down. Thrust is the upward force that propels the aircraft forward, while weight is the downward force of gravity that pulls the aircraft towards the ground. For drone, lift is generated primarily by the rotors. As the rotors spin, they create a pressure difference above and below the drone, resulting in an upward lift force. For drag, drones experience drag as air resistance against its body and rotors. The design of the drone can minimize this force, but it is always affected, especially at higher speeds. Thrust is generated by the motors driving the rotors. It's generated by the motors driving the rotors. By increasing the speed of the motors, a drone can increase its thrust, enabling it to move forward or in a desired horizontal direction. The weight includes the drone itself, its battery, and anything it carries. The amount of lift generated must be sufficient to overcome this weight for the drone to ascend. For planes, they achieve lift through the aerodynamic design of the wings. As the plane moves forwards, air flows faster over the top of the wings than underneath, creating lower pressure above the wing and higher pressure below. Thus, it lifts the plane. For drag, it encounters drag from air resistance against the fuselage, wings, and tail. High-speed planes are streamlined to reduce drags. Thrust is typically provided by jet engines or propellers, which propel the planes forward. The forward motion is crucial for creating the airflow over the wings necessary for lift. The weight of a plane includes its structure, passenger, fuel, and cargo. A plane must generate enough lift to counteract its weight to achieve and maintain flight. And lastly, for glider, similar to plane, lift is generated by the wings, although gliders rely on upward current like thermals to gain altitude since they do not have engine to provide continuous forward motion. Gliders also face drag, which is critical to their design. Since gliders lack engine, minimizing drag is essential for maintaining flight for longer durations. Gliders do not generate thrust in the traditional sense as they lack engines. Instead, they rely on initial launch methods like being towed by another aircraft or winched, and then they utilize air currents to stay aloft and move. A glider's weight includes its structure and any payload such as the pilot. The lift must be sufficient to counterbalance this weight, and the gliders are designed to be lightweight. They can stay airborne for extended periods of time. Next, we have Bernoulli's principle, which states that when air moves faster, its pressure becomes lower. This is important for understanding how planes and other flying objects go up into the air. For planes and gliders, the wings of planes and gliders are designed based on Bernoulli's principle. They typically have an airfoil shape with the top surface curved and the bottom surface flatter. As the aircraft moves forward, air flows over the wings. The curvature of the top surface causes the air to move faster over the top of the wing than the bottom. According to Bernoulli's principle, the faster moving air above the wing has lower pressure compared to the slower moving air below the wing. The higher pressure below the wing and the lower pressure above it creates an upward force, lift, which counteracts gravity and enables the plane to fly or glider to fly. For drones, the rotors of a drone also function similarly to airfoils. Each rotor blade is designed to have a shape that allows for differential air pressure. When the drone rotor spins, they create a difference in air pressure and above and below each rotor blade. The air moves faster over the top of the rotor blade, creating lower pressure compared to the underside. This pressure difference generates lift, which allows the drone to rise and stay airborne. Some key differences are that while planes and gliders rely on the forward motion to maintain airflow over the wings, drones can hover, ascend, or descend vertically due to the direct lift generated by the rotors. Planes typically require running engine to keep moving and generate lift. Gliders can use thermals, rising currents of warm air after an initial launch to stay aloft. Drones generate lift through the electrically powered rotation of the rotors. Next, we have the angle attack. The angle attack is the angle between the air coming towards an aircraft and the line on its wing or rotor blade. This line goes from the front edge to the back edge of the wing or blade. Basically, it is how tilted the wing or blade is against the air when aircraft move forward. For planes and gliders, the angle of attack is critical in controlling lift. As the AOA increases, the lift initially increases. This is because a higher angle allows wing to deflect more air downwards, producing more lift according to the principle of aerodynamics. In flight, changing the AOA is a primary method for controlling the aircraft's ascent and descent. For example, increasing the AOA can help the aircraft climb, while decreasing it assists in descent. For drones, in drones, the rotor blades act like small wings. The AOA of these blades is crucial controlling the drone lifts and movement. By changing the AOA of the rotor blade, a drone can increase or decrease lift and thrust. This allows it to ascend, descend, hover, or move in different directions. Drones can quickly alter the AOA of the rotor blades, making them highly agile and capable of complex maneuvers. Some key differences are that in most airplanes and gliders, the AOA is changed by altering the aircraft's pitch, nose up or down, using surface controls like elevators. In contrast, drones can use the AOA of each rotor blade independently, providing more direct and varied control. Managing the AOA in planes and gliders requires understanding and reacting to the aircraft's behavior, especially during takeoff, landing, and maneuvers. Drones, often controlled electronically, can adjust the AOA more quickly and precisely, sometimes automatically with computer assistance. A stall in aerodynamics refers to a condition where an aircraft's wings lose lift due to an excessive angle of attack. This phenomenon is primarily relevant to fixed-wing aircraft like planes and gliders, but is less applicable to rotorcraft like drones. The cause of stalls in planes and gliders can occur when an AOA between the wing's chorus line and the oncoming air, which increases beyond a critical point. At this excessive angle, the smooth airflow over the wing's upper surface becomes turbulent, drastically reducing lift. The loss of lift during a stall means the aircraft can no longer contact gravity effectively, which can cause it to descend or lose altitudes. Pilots must lower the AOA, often by pointing the nose of the aircraft downward to regain smooth airflow and lift. Drones operate on rotorcraft aerodynamics using rotating blades of rotors to generate lift. Each rotor acts independently to create lift, unlike the fixed wings of planes and gliders. Traditionally, stalling, as it occurs in fixed-wing aircraft, does not apply to drones because they do not rely on forward motion through the air and the fixed-wing angle of attack for lift. While drones don't stall in the traditional stance, they can lose lift or control due to rotor failure, power issues, or extremely aerodynamic conditions like very high winds or aggressive maneuvers. The key difference lies in how these aircraft generate lift. Planes and gliders use fixed wings, where the lift is highly dependent on the wing's angle of attack and forward motion. Drones use rotating blades, where lift is controlled by the rotor speed and orientation. Pilots of planes and gliders must be vigilant about the angle of attack to prevent stalling. Drone operators, however, are more concerned with rotor functions, power levels, and external functions like wind.
Hi, I'm Huang and Chieh, and I'll be covering our group's Unity implementation. So the goal here is focus on implementing realistic flight for planes while making it easy for players to control. I'll be discussing about how planes are able to fly and steer, what are the forces and motions of flight, and how do they affect the plane's movement, and lastly, how it can be implemented into Unity 3D. To start, we need to understand how a plane is able to fly in real life. Planes are able to take off by generating a force that pushes them forward, known as thrust, from their engines or propellers, which allows them to gain speed. While the plane is moving forward, there's an opposing force known as drag, which is the air resistance that will slow the plane down. Gravity and the mass of the plane are also constantly pulling the plane down. As the plane continues to gain speed, their wings will start generating a lift force, and if the lift force generated is more than the opposing force of gravity, the plane will be able to lift off the ground and fly. The amount of lift force generated depends on the angle of attack, or AOA. AOA is the angle between the direction where the plane's velocity is pointing and the direction of where the plane's nose is pointing. A larger AOA will generate more lift up to a certain point where it will enter the stall region, which causes the plane to drop. Next, we need to find out how a plane is able to steer while airborne. Planes have many control surfaces that create an imbalance of lift, which is what allows them to turn or rotate. On the wings are the ailerons. On the horizontal stabilizers at the rear of the plane are elevators. And lastly, on the vertical stabilizer or stabilizers is the rudder. Elevators are responsible for pitching the plane up and down. They are able to generate more or less lift force acting on the plane, which causes the plane to pitch upwards or downwards. Next are the ailerons. A plane is able to roll when its ailerons are moving in opposite directions. When one of its ailerons is moving upwards and the other is moving downwards, this will result in an imbalance of lift, which causes the plane to roll. Lastly, rudders generate lift force which pulls the rear of the plane sideways, causing it to yaw left and right. Now let's talk about how we can implement realistic flight for planes using what we learned into Unity. Firstly, we need to add a rigid body to our plane object so that it can be affected by physics in Unity. We have to set the mass, drag, and angular drag in the rigid body while making sure that used gravity is checked. We can also add colliders to the plane so that it's able to interact with other objects in the scene, such as obstacles or a runway, in order for it to take off. Before setting up player input, we have to add new input keys for players to control the plane's yaw. This can be done in Unity's input manager. Next, we'll handle player input using a player controller script. We will need to handle inputs for roll, pitch, and yaw. We can also allow players to increase or decrease the plane's throttle in order to speed up or slow down. In real life, the control surfaces of a plane creates lift force that changes the plane's orientation. This change in orientation will affect how all of the control surfaces produce lift, which makes the plane more difficult to fly. For example, a yaw input is supposed to only rotate the plane around the y-axis, but since the rudder is above the plane's center of mass, it will also create a slight roll, which makes the plane wobbly and more difficult for players to control. So a solution is to add forces directly to the rigid body of the plane. This helps to keep the code simple and easy for players to control. We also need to call the forces applied to the plane in the fixed update method so that they are updated more frequently to ensure smooth flight movement. A camera system that is able to follow the plane in the first or third person view needs to be implemented so that players are able to maintain a clear view for different situations. This can be done using a camera controller script or using Cinemachine, which is a Unity package for camera tools. And in order to add more realism, we can implement visual and audio feedback for players. For visual, we can make the propeller spin based on speed and time elapsed, or add wing trails using trail renderers. For audio, we can add sound to the propeller when it's spinning, or a sound for the engine starting. To summarize, learning and understanding the concepts and physics behind how flight is achieved in real life is crucial before implementing it into Unity. It is also important to keep in mind that the implementation is easy for players to follow and control to ensure a smoother experience for players.
Hello, this is the case studies for Group 7 who is doing the topic of flight. My name is Xavier and I'll be covering the case studies now. First off, a brief overview of how flight is used in games. Some games use flight as a side feature that enhances or adds excitement to their already polished game, while others make use of it as a core mechanic. An example of the first are Fortnite and Star Wars Battlefront 2, and an example of the latter would be Breath of the Wild. First, let's cover Star Wars Battlefront 2. Star Wars Battlefront 2 has dogfighting as a side mechanic. You control TIE fighters or X-Wings, which are equivalent to planes, and you attempt to shoot down the enemies on the other team. In this game, flight comes in the form of vehicles. These vehicles, if left unchecked, can shoot down troops on the ground and change the course of the battle. It provides a sense of depth to the game and makes the game more realistic. Some challenges that the developer faced was the complexity of space combat. Space combat allows the player to move in a multitude of ways, an example being that planes are able to fly upside down, which may be disorientating for some players. In order to fix this, they added auto adjustments like rotate feature to the game in order to make sure that players have an easier time. However, if players were so inclined and wanted to improve their skills, or they had the necessary skills, they could turn off this feature and enjoy space combat to its incredible degree. Next, we have Fortnite. Fortnite's Jetpack was added to the game in its 4th season. It functioned like a regular jetpack where the player will be propelled upwards with limited movement over spaces. Before the jetpack, players had to rely on their building skills to gain any sort of advantage in the air. The jetpack meant that players had to be aware that the opponents could take into the air at any moment, and it also reduced the skill ceiling that was required, as now players could gain an advantage in the air without having good building skills. It opened up new tactics and styles of play in what was originally a grounded game. When adding a new item to the game, especially one as game-changing as the jetpack, measures had to be taken. This was because not only would it affect gameplay, but interactions with other items also caused problems. Some examples being grenades that allow the player to change their speed and their height incredibly fast, which would propel the jetpack to unforeseen heights. In an attempt to balance this out, the developers chose to make the jetpack have a limit on its usage, as well as vault the jetpack, which means that it went away after this season. Next, we finally have Breath of the Wild, which features paraglider as its flight mechanic. Paragliders in Breath of the Wild is one of the player's main modes of transportations alongside walking on foot as well as horses. In this game, this mechanic has many usages, some examples being transport, puzzles, and exploit. I will go more in depth on Breath of the Wild now. Firstly, to understand how Breath of the Wild implemented its gliding, we have to understand how gliding works in real life. Normally, flight of planes and the like are affected by 4 factors: thrust, lift, drag, and weight. However, since a glider lacks a propulsion system like an engine, it means that thrust is no longer involved in the glider. As such, gliders can't really maintain themselves in the air, which means they need an external force to maintain themselves, in this case being the person that hangs onto the glider. To simulate realistic movement, the paraglider in Breath of the Wild falls slowly regardless of player movement in any direction. This has the added effect of balancing Breath of the Wild's glider by the fact that you cannot traverse too far on a glider without falling to the ground. Some ways that smooth animations could be ensured during this gliding would be a blank tree. A blank tree allows for animations to blend and move smoothly with each other without having to provide additional animations for movement in between, as those are automatically generated based on the animations already provided. For controls during gliding, they should have a button that allows them to move forward and backwards, as well as two left and right buttons that control the rotation of the glider. An additional button is required to open and close the paraglider. An example can be seen here. The speed of the glider is also affected by the movement speed of the player in Breath of the Wild. If the player has a high movement speed, the force will be carried over to the player, propelling the player forward. When the glider is closed, the player should start falling like normal, but when the glider is open, the glider should apply an upward force to the player again, halting the player's fall. Or you could reduce the gravity that is affecting the player, which is shown in the code segment here. The force added, of course, must be lesser than gravity so that the player will continue to fall but at a slower speed, replicating the motions of gliding. Okay, now let's talk about how external mechanics also are tied in with gliding. Okay, and one key mechanic that is tied in with gliding is the stamina mechanic in Breath of the Wild. The gliders are controlled by this fact, as stamina is depleted while the glider is being used. As they progress through the game, stamina can be earned and increased, allowing the player to fly further if they so wished. This means that if there was an area in the game that the player could not get to earlier, it would be accessible later on in the game. Oh, of course, we can't forget the level of height in Breath of the Wild. You must be at a certain height to open the paraglider. And an example of how this might be implemented would be using a ray cast with a limited ray length pointing downwards at the ground. If the ray cast is not in contact with the ground, that enables gliding. Of course, you could use other methods such as character controllers and check if the player model is grounded or not. Now, turning back to how external mechanics were affected, puzzles were also one of the things affected by gliders. With the freedom given to players with the glider, developers had to consider how to design their puzzles. In order to ensure that flight just wouldn't invalidate puzzles, they made sure to at least design each puzzle with at least 3 solutions in mind, which allowed for player flexibility and new ways of clearing the puzzle. The weather also had to be taken into consideration while gliding in Breath of the Wild. As during rainy days, stamina would decrease faster, which means that the distance that players could glide would be reduced, which means that players had to consider the weather as a factor when they chose to glide. Of course, we can't forget about other external forces, such as wind generated by fire, which would propel the glider upwards, or depending on the direction of the fire, into the air. Fans can also be set to push players across the map, which led to interesting puzzle combinations by the developer. In conclusion, the developers of Breath of the Wild had to give a lot of consideration to how gliders would work beyond the base mechanics. The freedom and accessibility the glider provided with the external mechanic made the glider in Breath of the Wild very unique and fun to play with. That's it for my presentation and my case studies. Thank you very much.
Hi, I'm Huang and Chieh, and my implementation will be focused on realistic flight for planes and adding a control system for players. So this is how it looks like in the game scene. Players can increase the throttle by holding onto the spacebar, and they can decrease it by holding onto the left shift key. As the throttle is being increased, the propeller will start spinning. And when there's enough throttle, the plane will lift off and start flying. Players can pitch up and down by pressing the W or S key. They can roll by pressing the A or D key. And they can yaw by pressing the Q or E key. I've also added an extra functionality where they can switch cameras by pressing on the C key. Now I'll be going through some of the components used for my plane. So first I added a rigid body. Here I set a value for the mass. Also set the drag and angular drag to 1. And also check the use gravity box so that it will be affected by gravity. I also added an audio source to the plane for the propeller sound. I also added individual colliders for the body, the wings, and the wheels of the plane so that it will be affected by the other objects in the scene, such as the runway in order to take off. I also added some throw renderers to the end of each wing to create the wing throw effect. Here I have some Cinemachine virtual cameras for the camera system. Now I'll be explaining my code. So starting with the player controller. Here I have a sensitivity modifier, which is meant for fine-tuning the sensitivity of the player input based on the mass of the rigid body. Here the on enable and on disable functions are meant for switching between the cameras, which is managed in the camera manager script. So first I made a static list of all the virtual cameras, and in the isActive camera function is to check if the camera is currently active. And because in Cinemachine, if the camera has higher priority value, it will be prioritized first. So here we set the new camera to a higher value. And in this, for each function, it will iterate through the cameras and set the priority value of the non-active cameras to 0. And here's for registering and unregistering each camera. Here in the awake function, we will get the rigid body, the engine sound audio source, and the propeller object. In the handle outputs function, we will get the player inputs for roll, pitch, and yaw. The inputs for yaw were added in the input manager. So here is to get the player input for increasing and decreasing the throttle. For the engine sound volume, it will be based on the throttle, and it will be clamped between a minimum and maximum volume. Same for the throttle value, it will be clamped between 0 and 100. And I've set the propeller speed to be based on the throttle value. Here in the update function, we handle some of the player inputs. The increase and decrease throttle will handle the throttle increments. So for the plane movement, first is the thrust function. A force will be added to the rigid body, which will take in the transform forward, max thrust, and throttle values. For pitching, a torque will be added to the rigid body, which takes in transform right, pitch, and the sensitivity modifier. For the roll, there will also be a torque added to the rigid body, which will take in negative transform to forward, roll, and the sensitivity modifier. For yaw, torque will also be added to rigid body. And lastly, for lift, an upward force will be applied to the rigid body, which will take in vector 3.up, velocity and magnitude of the rigid body, and lift. Lastly, all the methods that handle the plane physics and apply force to the rigid body will be called in the fixed update method to make sure that it's updated frequently to ensure a smooth flight movement. And finally, for the propeller rotation, it will be handled in the propeller script, where it will rotate locally around the y-axis based on the speed and time elapsed. The main problem that I came across was trying to implement the individual control surfaces of a plane, such as the ailerons, the elevators, and the rudders, to achieve a more realistic flight. I realized that it would be difficult to implement, as each of the control surfaces will have to produce its own lift force. And since the lift force produced by each of the surfaces are not from the center of mass, the plane will become difficult to control. So instead of trying to produce lift force from different control surfaces, I decided to just add forces to the rigid body. This made the code and the implementation easier, and also easier for players to control. That's all for my implementation. Thank you.
So this is my implementation of flight for Unity. And in this case, I am doing the glider mechanic. First off, I have the plane here and simple controls. I will show them off now. In a simple method, I have rotation of the plane, which is done using the left and right keys. I have move forward and move backwards, as well as the gliding and an increased speed whenever I need it. Okay, first off, let me cover the normal on the bottom left. What this will show is when the plane is in gliding and when it is not gliding. Currently, it is not gliding, so normal gravity is weighing down on the plane. When I run through the plane, you can see on the number in the transform here that it falls down slowly. Roughly 5, 6, 7, 8, 9, 10. Okay. And it is also affected by the plane's speed. If I were to increase the speed by pressing shift and go forward, even with normal gravity, covers a bigger distance than if I were to do it without the speed boost. Next, I have the gliding mechanic. When the player controller here isn't grounded and it is in the air, and I press spacebar, you will see the normal turn into gliding and the gravity decreasing. The height of the plane decreases slower compared to when normal gravity was acting on it. If I were to press shift currently, it will increase the speed of the plane as well, showing that external forces affect the glider. Here, I will increase the speed. And you can see from the bottom right, you can see here that it falls slower. If I were to let go and it changes back to normal, it falls faster and faster. Okay. Now, I will show off the code. Okay, so besides all the camera, I will show you how the plane handles its inputs. Firstly, we declare all the needed parameters here, and we declare a new private and velocity. We start by getting the character controller, and then we call the two methods handle input and move in the update function. What this does is every frame that the game runs, it will run these two functions in a row. Firstly, we have handle inputs, which serves the purpose of getting the inputs from wherever the player has pressed. In here, I have the input for left and right, and the input for shift. If you press down shift on the keyboard, what it does is double the speed. This is the gliding, the one for gliding. If input key down space, which means that if you press space and character grounded is not true, which means that it is in the air, then I'll set glider equals to true. The speed will increase, and yeah. Then if the space key is released, glide becomes false, which means the function becomes inactive. Now, in the move function, we have the regular rotation and we have the movement. This handles rotation of the character, and this moves the character forward. This is the line of code that calculates how fast the thing is, and speed is normally changing depending on whether left shift is pressed down, which means that the walking speed will be changed. And now we have this. If glide is active, so if the space button here is pressed down, then glide will activate. Otherwise, we apply gravity. Okay. And now for gravity and glide, they have similar functions, except that only when glide is activated, then the gravity is lessened, which is what this class does. And also to ensure that the code doesn't go into a loop of decreasing gravity each and every time update runs, I set if gliding equals to false and gliding equals to true, which means that once this runs, gliding will be set to true, which means that every time update happens again, this will work. If gliding, it won't continuously remove. Yeah, that's it for my implementation. Thank you very much.